Okay. What does this one say? It's a graph. It says figure 3 shows the concentration of oxides of nitrogen in the atmosphere during one day in a city. Concentration of in micrograms per cubic meter. Okay, and those were the different times they were recorded. Okay, so it looks like there was a spike, and that's what it's talking about, the concentrations. Okay, scroll down. Let's look at the question well. It says, which two times have the highest concentrations of oxides of nitrogen in the atmosphere? Okay, so from this graph, what would those times be for you?
Um, 9 a.m. and 5 p.m.
Exactly. 9 a.m. and 5 p.m. Those were the peaks in this graph. Yes, that's fine. Okay, what else does this say? Suggest why there are highest concentrations of oxides of nitrogen at these times. So 9 a.m. is usually when people I don't know. I'm just trying to think now. Most people start go to work, get to work about that time, and close about that time. Do you think there's anything in human activity that could suggest the rise in oxides of nitrogen? I'm just thinking, typical 9 to 5 jobs. Yeah, I'm just thinking, could there be a relationship between when work starts in the day and when people close for work in a day? Okay, just thinking. Okay, so let's just see, what does the marking scheme say?
More cars, buses, lorries on the road.
Sorry, I didn't get that. More what?
More cars, buses, or lorries on the road. Trucks.
On the road. Okay. At those times, right?
Oh, yes.
Okay. I guess that agrees with our deductions, because those will most likely be the times people are getting to work, so there will be traffic. Okay, that makes sense. Okay. And then 5 p.m. will be when they are leaving work and going back home. All right, so let's move on. It says this question is about fuels. Coal deposits were formed from the remains of trees. Okay, yeah. It says name the process in the leaves of trees that uses carbon dioxide. Okay, that would be photosynthesis, right?
Yes.
Okay. The next one says, how is coal formed after trees die? Trees are burned, trees are compressed, the trees are melted. I would go with compressed. So what does the marking scheme say?
Yes, it's compressed.
Okay. All right. So actually, the idea that where I got the idea from was the fact that crude oil that's formed under the earth between plates of sedimentary rocks is actually as a result of them being between those rocks. So that kind of crushes them, and yeah, leaves fossils that form crude oil later, compounds of carbon. Okay, so I think we can move on. So what does it say? The next one says something. Coal contains small amounts of sulfur. What does it say next? Name the gas produced when sulfur burns in oxygen. Okay. Sulfur burns in oxygen to give us sulfur. We can just call it sulfur dioxide. Okay. Yeah. Sulfur dioxide. So what does the marking scheme say?
Oh yes, it says sulfur dioxide.
Okay. Uh, okay, so it makes sense, right? Sulfur is S, oxygen is O. So if you have sufficient amounts of oxygen, you would have SO2, just like you have CO2. Okay. Okay, so let's move on. It says, give two problems caused by the gas produced when sulfur burns in oxygen. Two problems. Okay. So the gas produced when sulfur burns in air. So this is what happens, right? We know that air has hydrogen in it too. So, or water vapor rather. So when SO2 combines with the water vapor in air, right? This is what happens. Just imagine this in your mind's eye. H2O plus SO2. Okay? H2O plus SO2. H2O being water vapor, SO2 being the gas formed when sulfur burns in oxygen. What do you think is going to give you? Remember, H2O plus SO2. What do you think the product will be?
Like what would happen?
Yes, what will be the product? What's going to, you remember how chemical reactions occur, right? The product, the reactants leading to the product. So the reactants in this case are H2O and then plus SO2. So what do you think the product would be?
Acid.
Yes, it's going to be an acid. Now it's not sulfuric acid. It's I've forgotten the name for it, but it's going to be H2SO3. Did you get that? H2SO3, because you already had SO2 with sulfur dioxide. So with the O coming from water, the water vapor, you now have SO3, H2SO3, which is very close to H2SO4. Okay, so yes, you would have an acidic combination, which can be harmful to the skin and also a pollutant harmful to plants. So but yeah, so but I'm not sure which of other problems the marking scheme highlights, but those are the two I know. Skin, it could cause issues, and then because of the acidic nature, and then it could also affect plants negatively. So what does the marking scheme say?
It says acid rain.
Exactly. Yeah.
Respiratory problems.
Respiratory problems. Okay. That's for humans and probably animals. Okay. Is that all?
And then also saying some sulfur dioxide.
Okay. Okay. All right. Okay. All right. So acid rain, of course, it makes sense, right? That's the whole idea. Water vapor combining with the sulfur oxide. Okay, let's move on. Okay, the next one looks like a figure, a graph. Figure 4 shows the relative amount of electricity generated from different fuel sources in the UK from 2012 to 2018. Okay, so that's the key to help us know which one is which. All right, so let's go to the question straight. It says, describe what happens to the amounts of fuels used to generate electricity in the UK. What happens to the amount from 2012 to 2018? Okay, to be very
Can I say my answer?
okay. Sorry, my internet went off for a bit. Can you hear me now?
Yes.
Okay, sorry. Okay, why are you trying to explain it?
No. I just yeah.
Okay. Okay, so what I would say, what I would say I observed, right? It looks to me that um, amount of electricity generated from other sources somehow stayed the same, right? From 2012 to 2018, and so did amount of electricity generated from nuclear fuel. Okay, those two seem to have stayed the same. Then when it came to amount of electricity generated by renewable fuels, right? I think I noticed there was an increase. Okay. Did you notice that too? Okay. And then finally, the amount of electricity generated by fossil fuels were somehow reduced from 2012 to 2018. Okay. So I think that's basically a summary of the diagram. Okay. So do you agree with my deductions?
Yes.
All right, cool. Okay, then let's move on. Okay. It says this question is about ammonia and its compounds. All right. Ammonia is NH3, by the way. Okay, we can see it there. And its compounds, NH4Cl, ammonium chloride. Okay. So a student heated a sample of ammonium chloride. Of course, you can see anytime you see one product, one compound on the reactant side, obviously there's nothing else that's going to happen than that product, that compound breaking down. Okay, it's going to break down into other things that would combine to make it up. And so we see here that NH4Cl is going to break down to give us NH3, that's ammonia, and HCl. So you can see that everything is complete, it's balanced, right? You have NH3 on one side and HCl on the other, making it complete, NH4Cl. Okay, so what does it say? One product is ammonia. What is the name of the product with the formula HCl? Okay, so you have an idea of the name of that product, HCl?
Hydrogen chloride.
Yes, correct. Hydrogen chloride. Yes. Okay, so let's move on to the next question. It says, ammonia is a gas, that we know. True. It says, what is the state symbol for ammonia? I mean, it's a gas, so definitely is G. Is G. It's not a liquid, so it can't be L. It's not aqueous either, so it's not in a fluid state. It's G. So we'll take the box G, the one that goes with gas. Okay. All right. So let's move on to the next question. It says, how does the equation show that the reaction is reversible? You know, I was just about to say this, and somehow I forgot. Now, can you scroll up? Let's see the equation again. It's saying how does the equation show that the reaction is reversible? Now, what does it mean in the first place for a reaction to be reversible? Do you have any idea?
Pardon?
What does it mean for a reaction to be classed as a reversible reaction? You have an idea?
You can reverse it.
It can be reversed. In what sense? Can you be more detailed?
No, I don't know.
Okay, so you are right, it can be reversed, but then if you just say it can be reversed, I mean, we could put so many different meanings to it. But to be more specific about what you meant, reversed just simply means that just like the left-hand side, the reactant gave rise to the product can also give rise to the reactants. Okay, so let me say it again. In a reversible reaction, right, typically in chemical reactions, typical chemical reactions are not reversible. I could give you an example. Sodium chloride, right? When you combine sodium with chlorine, as in sodium, the metal, with chlorine, the gas, you will get sodium chloride. That's table salt. You remember when we talked about table salt? If you heat table salt, there's no amount of heat you can heat a table salt that will make it go back to sodium and chlorine separately again. It's not possible. So in that case, that kind of reaction is irreversible. Most of what happens in the kitchen, okay, cooking food and all those things are irreversible reactions. Once food is made, there's no way. If we should I use an example now? For instance, swallow, right? there's no way that swallow can ever go back to being the form it was before it was made. Okay, or rice or any other thing you may class as food. So irreversible reactions are usually the order of the day, usually. But we also have another class of reactions that if you get the reactants together and they give you the product, if you leave those products together again, the products will take you back to the reactants. And guess what? It's like a cycle. It just goes on and on and on and on and on. So how do we know a reversible reaction? Can you see that arrow in between ammonium chloride and ammonia? Can you
Yes.
see it is going in two directions? That is what tells us that it's a reversible reaction. Just that. Once you see that kind of arrow in between there, you are safe. It's safe to conclude that the reaction is reversible. Why? It's going in both directions. The first arrow, the one on top, is saying that ammonium chloride can become ammonia plus hydrogen chloride. Or well, if it's in a liquid state, it could be classed as a gas. Sorry, as in aqueous form. Okay, because hydrogen chloride is an acid, hydrochloric acid. Okay, that's one. That's in the forward direction. Then let's look at the one that's pointing back towards NH4Cl, the one that's under, the arrow that's under, is saying that NH3 ammonia combine with HCl to give you ammonium chloride. So did you get the gist of that?
Yes.
Okay. All right. So you can see the answer to that question is that arrow, the arrow there. That's basically what tells us it's reversible. Oh, okay. So I'm sure you'll be thinking, why would they give you a good number of lines to write? Well, you could just smuggle in the fact that in reversible reactions, that arrow shows us that it's reversible, and reactants will give you products, and products too can combine to give you back reactants. Okay, so do you have any questions, or we can move on?
We can move on.
Oh, all right, so let's move on. Okay, it says the forward reaction is endothermic. You see these terms, quite interesting terms. The forward reaction is the arrow that's pointing towards the right-hand side. That's the first one. While the reverse reaction is the one that's pointing towards the left, the one underneath. So it says the forward reaction, that is ammonium chloride becoming ammonia and HCl, is endothermic. Now, there's a way I usually coined a way to somehow remember endothermic, because there are two. There's endo and there's exo. Okay, so endo. Let me start with exo. So exo is usually talking about outside something, external, exterior, ex this, ex that. Okay, so exo, EXO, okay, is talking about outside. So when you see exothermic, and thermic is talking about heat. Okay, so the whole idea is that an exothermic reaction is one that releases heat into its environment. Okay, so I want you to think about this. The reactants, when the heat of the reactants is usually less than the let me not mix it up now. Okay, so the heat of the reactant is usually more than the heat of the products. So this is the whole idea. The products are at a lower temperature. Why? Because heat came out from the reactants and went into the atmosphere. So just remember that exothermic talks about releasing heat into the environment. And of course, if endothermic is the opposite of exothermic, then endothermic absorbs heat from the environment. What does that mean? I want you to imagine for a moment, you have your hand around a box. Inside that box is a reaction going on, and that reaction is an endothermic reaction. The sensation your hand will feel is a cooling sensation. Why? Because it's an endothermic reaction. That means it will absorb the heat around your hands. And guess what? Your hands will feel cooler. Have you ever had that kind of sensation before, where you put your hands around something that's already cold? Your hand will feel cooler by touching that thing. And that what is really happening is that heat is leaving your hand and going into that thing. That's the reason why your hand feels cooler. Did you get the concept?
Yes.
Okay. All right. So it says that the forward reaction is endothermic. That means it absorbs heat from the atmosphere. So it now says, so the reverse reaction will be the opposite, exothermic. Okay. If one of the reactions is endothermic, obviously the opposite one will be exothermic. It will be the direct opposite of the other one. Okay, so just remember this. There's endothermic, and then there's exothermic. And exo stands for the one that endo talks about, the one that absorbs heat from its environment. Okay, so does the marking scheme add to what I just said, or it just tells us that it's exothermic?
Yeah, it just says exothermic.
Okay, all right. Okay, okay, so let's move on. So just for reference, let me just say something more about exo. Is it the orchid family? All those insects that have their skeletons outside them, like the cockroach, spiders, and the rest. Those ones have like their skeletons. They have like a skeleton outside that protects their bodies, their softer bodies. So those kind of skeletons are called exoskeletons. So just so that you can put a connection between exo in chemistry, exothermic in chemistry, and exo in biology. Exoskeleton, exothermic, outside. Always remember, exo means outside, outside, out. Okay. Okay. So we can proceed whenever you're ready. Okay. It says complete the sentence. Choose the answer from the box. What does it say? Equilibrium, okay, is reached when the forward and reverse reactions happen at exactly the same rate. Okay, the word is rate. It's not concentration, it's not temperature, no, it's rate. If you think about it, it's like speed. Yeah. Okay. All right, we can move on. This one looks more like reaction things. Figure 5 shows the reaction profile for the reaction with and without a catalyst. Okay. Okay, so we remember what a catalyst is. A catalyst is a substance that is introduced into a reaction, usually to help the reaction, to help to speed up the reaction. Okay, so typically the reaction without the catalyst would be slower most of the time. It would take slower time to get to its product, but with the catalyst will speed up things, by its action. So what does it say here? It says which letter represents the activation energy for the reaction with a catalyst. Oh, simple. All right, so maybe we should talk about activation energy before we go to the answer. Activation energy is simply the energy that has to be overcome in order for the products to start forming. Okay, so I want you to take a look at this graph. You will see that after letter B, after that line that signifies letter B, you see that there's, it's like a peak. The reaction goes all the way up. The graph, sorry, goes all the way up and then comes down. But then you can see that there's a second graph, okay? And that second graph is the one that shows that a catalyst was brought into the picture. How do I know? Because it's not as high as letter B, okay? So that's the whole idea. It's not as high as it. So this is what, this is the whole idea of the activation energy. So that peak that you see there is the first peak. The one for B is when there's no catalyst. Okay. The one for B is when there's no catalyst. While the one for C, let's say B, maybe I think we should say D. The one for D, okay, because D is actually the activation energy, the one that shows the higher peak. Whereas the one for C is the one that shows the lower peak. Okay, that actually shows you that the catalyst made it faster. So if we were to go with these options, I think the right one would be C. The letter, which letter represents the activation energy for the reaction with a catalyst? Okay, that would be C. Of course, the question had been flipped and said without a catalyst, the answer would be D. Okay. Did you get the explanation?
Oh yes.
Okay. All right. Okay, so we can move on. It says, give one reason why using a catalyst reduces cost. Oh, it says do not answer in terms of do not answer in terms of activation energy. Okay. Wow. Okay, so if you are not to answer in terms of activation energy, let's think about it, right? A catalyst would reduce costs. From my own opinion, let's imagine that the reaction involves using heat, right? Let's just use that example for instance. Now, imagine a reaction that uses heat. That means you would need, typically in those times, you would need gas. You would need what is called a Bunsen burner, right? Powered by gas, of course. It will get its supply from gas. And if you use a catalyst, remember what a catalyst does. It lowers the activation energy. But we're not saying this explanation in terms of activation energy. So the whole idea is that if a catalyst makes your reaction happen quickly, by lowering the activation energy, then that means it would cut down the amount of gas you would use, because it would go far, it will get to the product faster. Okay, so if I were to explain this without mentioning activation energy, I'll just say that catalyst helps us to get to the product faster, right?
Oh, just go for your own like this one.
What do you call it? The amount of gas used for a reaction that may need a burner would be reduced. Did you get that?
Yes.
Okay. Okay, but let's hear what the marking scheme says. Let's see if there's anything extra they said.
Increases rate of reaction, reduces energy required.
Okay.
Lower temperature can be used.
Okay. Lower temperature can be used, yes. So that's it. That's how it reduces costs. Okay. Okay, so let's move on to the next one.
You can be alright. You can be alright, short free kick.
Says ammonia is a mixture that is used as a household cleaner. Okay, all right. Ammonia is in a mixture. Sorry, I didn't see that in. What is a mixture that has been designed as a useful product called? Mixture that has been designed as a useful product. Okay. I'm thinking the right answer would be a solution. Okay. But what does the marking scheme say?
Formulation.
Formulation. Okay.
Yes.
Okay, formulation. I'm not sure about that term, but anyway, it works. So I was thinking solute plus solvent equals solution, but yeah, it's fine. Formulation. Okay. All right, let's move on then. Okay, let's see. What does this one? It's talking about an experiment. Figure 6 shows the experiment. It was done in a fume cupboard. Okay.
The MC. Who's the MC? Give Zane pen.
What's the question on this? Hydrochloric acid.
Give pen.
It says online for each type of variable to connect to. Okay. Time taken for the cross to no longer be seen. Volume of acid. Okay. So I think I'm looking at the dependent ones. The dependent variables are the ones that can change. Okay. So dependent would be the one that can change. The time taken for the cross to no longer be seen, that would be dependent. So I'll draw a line from dependent to that. Then the independent one would be the independent one. The temperature. Okay, so yeah, I'm not sure about it, but the temperature of the reaction mixture. Okay, there's volume of a flask. Okay.
Yeah, spin, please.
Okay, I'll go with temperature of reaction for the reaction mixture for the independent one. What does the scheme say?
It says dependent is time taken for the cross to no longer be seen. Independent,
Okay.
concentration for sodium disulfate solution.
Oh, okay. Okay. Okay, that first one. Okay, that's fine. Concentration. Okay, so the temperature didn't come into the picture. I guess that one would also be a dependent variable. Okay. Okay, that's fine. But at least they agreed with us on the dependent one. All right. Okay, let's move on. Okay. The experiment is at room temperature. Okay. It says, what's the temperature shown on the thermometer in figure 7? Okay. If you were to read off that value, what would you read? What would you read in that from that thermometer?
19.5.
19.5, because it's just exactly at the middle of 19 and 20. Okay. All right. What does the next one say? Table 1 shows the students' results. Okay, so scroll up. Let's see table 1. Concentration of sodium thiosulfate. Could you scroll up? Okay, I can see it now. Okay. Concentration of sodium thiosulfate, which is independent, and this one is dependent on time in seconds. Okay. Seems as the concentration increases, the time in seconds reduces. Okay. All right. So what deductions are we supposed to make? It says oh, so that's plotting a graph. You can do that.
Am I in time? Or
Yeah, you can pick your shoe size.
it won't work on this song.
Yeah, I think we should keep it. You can plot the graph, right?
Yes.
Now, whenever we say line of best fit, right, it suggests to me that the points will not be exactly on a straight line. So you need to look for a line that is not too far from all the points. That's the whole idea. Okay. So some of the points will fall on the line, some of them will not fall on the line. So the whole idea is that if there are 2 points that don't fall on the line, they shouldn't be too far from the line from another 2 points that fall on the other side of the line. So just remember that whenever they say draw a line of best fit, it's always telling you that the points will definitely not be on a straight line, but you can draw a line that would favor all the points. Okay, so kind of be in the middle. Okay. Okay, so these other ones, this question would the next question, predict the time, will depend on your drawing of the graph. So I don't know. Okay. But so maybe we'll have to leave that one since it's dependent on the graph. Okay, but we can say something about the next one where it says complete the sentence. As the concentration of sodium thiosulfate solution increases, the time taken for the cross to no longer be seen reduces, right? You want to check the table again?
What are you doing, Israel? Bring it back again.
Do you want to take a look at the table?
It doesn't show it. It doesn't show it. It doesn't show it. Oh, sorry.
No, you want to? Okay, let's take a look at the table. So just look at it. Concentration of sodium thiosulfate. Look at the numbers from 0.1 to 0.2 to 0.3 to 0.4. That shows an increase, right?
Oh, yes.
Now look at the time in seconds. Did you notice that it's reducing? From 82, it goes to 40. From 40, it goes to 20. From 20, it goes to 13. Then 10. Then 8. So can you see it's actually reducing?
Yes.
So it's safe for us to conclude that as the concentration of sodium thiosulfate increases, the time in seconds reduces. Okay, so are you good with that?
Yes.
Okay. All right, so I think we can move on then. Okay. Okay, this one says it's a calculation. It says in one experiment, 0.725 grams of sulfur is produced, in 20 seconds. What does it say next? Calculate the mean rate of the reaction from 0 to 20 seconds. Mean rate of reaction is given by mass of sulfur produced in grams over time in seconds. So Can you quickly crunch that with your calculator? 0.725 over 20.
Zero point 0.03625.
Okay. 0.03625. Okay. And I think it has a unit, right? The unit would be grams per second. Yeah, it should be grams slash seconds. That's what the unit would be. Okay. Let me see if I can send it in the chat box. What the unit should be. That would be small letter G /
Oh shit! Watch me shit. No, you were given chat.
Okay. Or G S raised to power minus -1. Okay. All right. So take a look at what I sent in the chat box. See if it resonates with you.
Church. That road, who is this guy? Oh, Andrew.
That's the unit, right? Does it agree with the marking scheme?
Yes, the G/S.
Okay. Okay. Let's proceed then. Okay, let's move on. Yeah. Okay, it's up now. Okay. Since the student did the experiment with 0.15 mole per dm cubed sodium thiosulfate solution and repeated the what? The experiment 3 more times. 1, 2, 3. 3 more times. Okay, that's 4 altogether. Okay. It says calculate the mean time for this reaction. Do not include the anomalous result in your calculation. Okay, so do you understand the meaning of that term, anomalous? Hello, Noah, you there?
Yes.
Yes, I was asking, do you understand the meaning of the term anomalous?
No.
Okay. So it's, well, you could say a safer word is to use the word abnormal. Okay. It's not a normal trend. So if you look at those values for test 1, test 2, test 3, and test 4, the one that seems out of place is test 3. Do you agree with that?
Yes.
Mm-hmm. You can see the others are hovering around 60 something, 60 something, 60 something, and test 3 is saying 80 something. It's way off the mark, kind of. So if they ask you to calculate the mean time, this is what you're going to do. You're going to say 60.5 plus 62.2 plus 65.7. When you add it and you get your answer, divide it by 3. Okay? Did you get that?
Yes.
Okay. So that's the mean. And remember, another word for mean is average. Okay? Take note, we're dividing it by 3 because we didn't use the fourth one, which is 82.3.
Listen.
So, were you able to calculate it?
Yes, 63.133.
Okay, 63.133. Cool. And it's in seconds.
Yes.
Okay.
63.1.
Yes, 63.1. Since it's 3 significant figures, yes, correct. Okay. So let's move on. Hydrocarbons. Okay. Looks interesting. It says figure 9 shows a hydrocarbon. Okay. What are the questions about figure 9? It says complete the formula for the hydrocarbon shown in figure 9. It's pretty simple, isn't it? What do you think would be in the space after C? And what do you think would be in the space after H? C what, H what?
C3, H, H8.
Yes, H8, right? I hope it was H you said.
Yes.
Okay, yes. C3H8, you're correct. So the next big question, what is the name of the hydrocarbon in figure 9? Any idea? Any idea? Propane, yes. Okay, so let's remind ourselves of the names. The very first one in the series would be methane. Okay, and that is suggestive of one carbon atom. The next one would be ethane. That is suggestive of 2 carbon atoms. The third one, the one that we just saw, is propane. That would suggest 3 carbon atoms. After 3 carbon atoms, you have butane. That is for 4 carbon atoms. Let me see how far we can go. After 4, we have pentane. That's from pentagon, okay? That's 5 carbon atoms. After pentane, what do you think we'll have?
I don't know.
Hexane, okay? Hexane, that would be 6 carbon atoms. And then for 7, that would be heptane. That's for 7. For 8, that would be octane. Okay, don't worry, I'm sending it to you via the chat. And then for 9, that would be nonane. And then for 10, that would be decane. That's for 10. Okay, so you could check your chat box. I just sent you. Okay, from 1 to 10. Sometimes we need to project what are the possible questions that could be asked in another year. So yes, that's the whole list from 1 to 10. So
the game. Where's everybody going?
so you're good with that, right?
Yes.
Okay. All right. Okay, let's move on. What does it say next? It says, which homologous series does the hydrocarbon in figure 9 belong to? Obviously, it's an alkane, right? When they ask you for homologous series, that's what it refers to. But please confirm the marking scheme so that we're sure we're on track.
It says alkanes, yes.
Yes, alkane. Okay, so just to be on the safe side again, alkanes is the one we just saw. It another possible one could be alkenes. So let me see if I can list the main ones. Alkanes are given by C N H 2N plus 2. Okay, then alkenes are given by CN H2N, yeah, and then alkynes are given by CN HN. Okay. What this says, is the number of carbon atoms. Okay, so just imagine alkane is typically given by CnH2n plus 2. If you try it out with this example we just saw, what would you notice? C3H2 times 3 is 6. 6 plus 2 is 8. You can see it agrees. Okay, so that's for alkanes. Alkenes, on the other hand, are CnH2. No plus 2, no minus 2, just CnH2n. And then finally, alkynes are CnH2n minus 2. Okay, so I hope those names sound familiar, right?
Yes.
Okay. All right. Okay, so yeah, I think we can move on. Okay, it says 30 grams of another hydrocarbon contains 24 grams of carbon. Wow, that means it's just 6 grams of hydrogen left in it. Anyways, what does it say? Which calculation gives the percentage of carbon in the hydrocarbon? Well, that would be 24 over 30 times 100 over 1. And the only one that looks like that is the third one. Do you agree?
Yes.
Do you agree with that?
Yes.
Okay. All right. So the others want to look like it, but are not it. They are wannabes. Okay. Okay. So if you are good with that, we can move on. It says, I'm sorry, table 3 shows boiling points of some hydrocarbons. Okay. CnH2, is that H6? Okay, boiling point. Okay. It says, describe how the boiling points change as the number of carbon atoms in the hydrocarbon increases. Well, what would you safely conclude? Does it increase or does it reduce?
Increase.
Now, if you are asked, why do you think it increases? What would you say?
The further down you go, the higher the boiling points become.
Okay, I didn't get what you said. Could you come again?
As the number of carbons increase, the higher the boiling point increases.
Okay. Yes, the boiling point increases. But can you point to why that happens? Now, just think about it this way, right? Boiling point involves turning, what do you call it? It's the point at which a liquid becomes a gas, right?
Oh, yes.
So what does that suggest to you? The molecules in the liquid become freer when they become a gas, right? Now,
yes.
for a molecule to be free, it means that the energy, it needs to absorb enough energy, enough heat, and to be more specific, it needs to absorb enough heat energy, enough for it to break away from its bond with the other molecules. So That's the reason why it will become freer after the boiling point exceeds. So now what it now means is this. There's a stronger is that right? Is it inter or intra? I'm not too sure. But you understand what I'm trying to say, right? The bond between the molecules of, for instance, ethane, the first one, they are much stronger than the bonds between the molecules of the second one, which is C4H10, of course. And it's very, very obvious that the bonds between C6H14 are even much stronger for the boiling point to go higher. So just imagine that the boiling point keeps on increasing, keeps on increasing. It means you will need more heat to break those bonds, isn't it?
Yes.
Uh-huh. So when you are explaining how the boiling points change as the number of carbon atoms increase, you might want to just mention that. Or let's see, they might ask you why you think it happens like that. Then you would now want to explain further. Okay, but you got the concept, right?
Yes.
Okay. All right, let's move. Okay, so here we go. Hydrocarbons can be cracked. Okay. It says give one condition used to crack hydrocarbons. One condition. Okay. So the whole idea of cracking a hydrocarbon is usually to break it down into a smaller molecule, right? A bigger molecule is being cracked to break it down into smaller molecules. So I think one condition would be that the molecule of the hydrocarbon that is being cracked has to be a big one. Okay? There will be no point cracking a small one. I mean, what are you trying to crack it into? You understand? So basically, we're cracking big hydrocarbons that have big molecules. What I mean by big molecules are, something like the number of carbon atoms in it is usually huge, something like 20. Just imagine a hydrocarbon that has 20 carbon atoms in a single molecule. Okay, so cracking it would involve breaking down that 20 down into smaller molecules like C4, C6, C8, stuff like that. Okay, but let's see what the marking scheme says. What does the marking scheme say for this question?
High temperature, steam, high pressure,
Okay.
low or no oxygen in atmosphere, and
Okay.
aluminium.
Sorry, I didn't hear.
Aluminium oxide.
Aluminium oxide. Oh, okay. So it's talking about the conditions for the reaction to happen. Okay. Okay, I get it now. Okay, that's fine. Okay. So high temperature is required. Yeah. Yeah, that's fine. Okay, so we move on. It says balance the equation for cracking C6H14. Okay, so you want to break that down? You want to balance that? What do you think will be in front of that C2? Now, take a look at, okay, let me just wait for you. Go ahead. Can you see anything there?
Is it 2?
Yes, it's 2. So let's take a look at it. On the left-hand side, you have 6 carbon atoms. On the right-hand side, they must also add up to 6. Now, clearly, they didn't put any numbers to be put for the first one. So that means we only have 2 carbon atoms from C2H6, but they must be 6. For you to have 6, that means you need 4 more. And meanwhile, you already have C2 on this side. Now, I hope you notice that C2H6 is ethane, while C2H4 is ethine. Okay, just fun fact, just so that we'll, in case they start asking what's the chemical name for the product. Okay, C2H6 is ethane, while C2H4 is ethene, not ethine, ethene, because of the C2H4, CNH2N. Okay, so yes, if you put 2 in front, then you will have 2 times 2 to make C4, and then 2 times 4 to make H, 8. And 8 plus 6 is 14. Everything balances out. Okay, so you are correct. All right, so what does it say next? Give one reason why hydrocarbons are cracked. Okay, so typically it's to help produce smaller hydrocarbons which would burn faster. Okay, which would burn faster and as fuels, more efficient fuels. Okay, if a fuel burns faster, then that means the engine can quickly access the energy that comes from it. Okay, all right, but let's see what the marking scheme says. That's my own understanding of why hydrocarbons need to be cracked. Smaller molecules will burn faster, hence more efficient fuels will be produced for the engine. All right, so let's see what the marking scheme says.
It says used for wood, uses less energy, uses less coal or oil, produces less waste, renewable / sustainable.
Okay. Yeah. Sustainable, efficient. Yes, that's good. Okay. It says window frame can be manufactured from wood or plastic through. It says table 4 shows the results of a life cycle assessment for making what is that? Okay, 1 wooden and 1 plastic window frame. Okay, life cycle assessment. Interesting. It says that both of them are of the same size. Okay, table 4. Okay, okay, copyright things. It says give 3 advantages of using wood instead of plastic in the manufacture of window frames. Wow. Okay, here goes. What's the advantage of using wood over plastic?
Look, the next two can't get man. Just shut up.
Pardon?
Do you want to give that question a try? 3 advantages of using wood instead of plastic.
Mason.
Did you get that?
Yes.
Beautiful.
Okay.
Beautiful. Get down.
So I think wood is much stronger, right? Do you agree?
Pardon?
Can you hear me now?
Yes.
Okay, I said well, first things first, wood is much stronger. Um, wood is stronger. What else? For a window frame, wood is stronger. And then
It's renewable.
it's what
Renewable.
is renewable. Okay, much environmentally friendly. I can't really imagine what a plastic window frame would be like. But I'm just thinking, just imagine if you have to fix it. I'm just thinking how you would even go about fixing it. So I think wood is more environmentally friendly than plastic. Um, yeah. Um, wood doesn't easily change what do you call it, shape in terms of um, exposure to heat. Just imagine heat from the sun and all that. And you have a window frame that's outside most of the time in the sun's glare and all that. So yes, I think those are the things I would say. I'm not sure I was able to get three advantages, but I think those are the ones and that come to mind. It's wood is more environmentally friendly than plastic. Two, wood would be able to withstand pressure to change shape more than plastic, especially in the face of heat. And then wood is more easy to, like you said, it's renewable. It's more easy to renew than plastic. All right. But let's hear from the marking scheme in case they have something different.
Yeah, they also just says less wastage, renewable.
Less wastage.
Yes, it's
Okay.
renewable.
Okay. 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 That's good. Okay. All right. Let's move on. A student investigated the colors of a brown ink using chromatography. All right. Figure 10 shows the apparatus used. Give two errors made by the student. Two errors.
He drew the line with ink.
Okay. Yeah. Okay. So you feel that line would cause some errors in his result, right?
Yes.
Mm-hmm. So that line is going to cause, is going to give it's going to create some errors in his result by somehow, the whole idea of chromatography is supposed to help you see the constituents of something. So in this case, the brown ink will show you all the things that are inside it by those things moving at different speeds. So the yellow color moves at a different speed from the green color. Green color moves at a different speed from the blue and then the red. But when you draw a line across them, then that line will have a way of modeling of things, and you'll not be able to get the exact readings. Yeah. Okay. Okay. What does the marking scheme?
Start line, no lid on the tank, surveillant will evaporate. Surveillant is above start line. Colors and ink will dissolve.
Okay.
Start line is in ink.
I'm open them right now.
Drawn in ink.
Okay. 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 Yes. Okay. Okay. So we need to be careful with our experiments. Alrighty. Okay, let's move on.
Now, Biscoff, let's talk about corner shop things.
All right, let's move on. Or are you writing it down?
Bruce.
Oh yeah, I'm almost done. Yeah.
All right.
Wait, no, Bruce. Bruce. Oh, no, I can't believe that. This is 85.
Okay. Okay. Figure 11 shows the result. Okay, I guess this one is a different one. It says give two conclusions the student can make from figure 11 about the four colors in the brown ink. Okay, two conclusions. The blue color travels faster than all of them, and the yellow color travels faster than the red one. I think the red is the slowest in terms of the speed. Okay. Okay, but let's see what conclusions they have there on the scheme.
The brown ink contains the color blue, yellow, and red.
Okay. Blue, yellow, and red. Okay. Okay, that's one conclusion. They asked for two.
The brown ink contains an unknown color. The Brown ink does not contain the green ink.
Okay.
Blue color is the most soluble. Red is the least soluble.
Okay. Okay. Blue is the most soluble, while red is the least, based on its speed. Okay. Okay. All right.
Look at it.
Okay.
Wait. Oasis is nice.
Okay. This says, why was the green color still
What about Miranda?
that line at the end of the experiment? The experiment was left for too long. The green color was insoluble in the solvent. Okay. The green spot contained too many colors. The green spot was too small. Okay. I think it's safe to say that the green color was insoluble in the solvent, right?
Yes.
Mm. Okay. Okay. It says a student calculated the RF value of a color to be 0.25, 0.24, sorry. The color moved from 1.8 cm, moved 1.8 cm from the start line. Calculate the distance the solvent moved. Use the equation. RF equals distance moved by color over distance moved by solvent. Okay, so let's see what this is going to play out as. RF has been given to us as 0.24. So I'm going to simply say 0.24. This is how the calculation will go. 0.24 equals 1.8 divided by x. X is the distance moved by the solvent, which we don't know. Now, whenever what you are looking for is in the denominator, okay, like in this case, it's in the denominator, right? This is what we're going to do. You would now say that x is equal to 1.8 divided by 0.24. It's as if the guy outside, the 0.24, takes the place of the x. Okay, so I'm going to show you what I have there, but you will help me crunch it on your calculator. Okay, so take a look at what I sent to you on the chat. 0.24 equals 1.8 divided by x. The x being what we're looking for, distance moved by solvent. Okay, can you see that?
Yes.
So you can see what I just did. It's as if the x and the 0.24 switched places. Okay, so this is what happens when whatever you're looking for is in the denominator. In other words, it's underneath. Okay, the one that's underneath takes the place of the guy that's on the left-hand side of the equality sign. That's just it. They just switch places. So when you punch it on your calculator, what do you have? 1.8 divided by 0.24.
7.5.
7.5.
Yes.
Okay. All right. Okay, so there you go. You have your answer there. I think we can go back to the questions now. Our time is almost up. Okay, let's see if we can do one more question to rope that in there for history today. Okay, so this one says, water that is safe to drink is called potable water too. Compare how easily potable water can be obtained from 1. Wastewater, that's sewage. 2. Groundwater, that's fresh water. Wow. Yeah, if you ask me, there's a huge difference, world of difference between wastewater that comes from the sewage, trying to get potable water, drinkable water from it. I mean, it's going to take a lot versus groundwater, fresh water. Fresh water is already is really closer, to potable water than wastewater because you have chemicals in wastewater. Sewage is everything that can come from the toilets, the kitchen. Just think about it. I mean, so many things are involved. There's waste, like chemicals that need to be gotten rid of. Then you now need to filter it again. Whereas for groundwater, if you use there's a particular filtration technique that you can use, and by the time you are done, I mean, you don't even need to boil the water. So in some scenarios, if you use that filtration technique properly, the groundwater can actually be um uh, taken as like clean water, okay, using just basic filtration technique. But wastewater, sewage that has to be converted to potable water would need a lot of effort and cash, okay, because you're going to have to buy chemicals to clean up, react with the waste that's there, take it out. Then at the end of the day, you still have to boil the water because of all the microorganisms that are in there just to make it potable. So um, there's a lot going on for wastewater than groundwater. Okay, what does the marking scheme say?
Groundwater, easier to obtain, fewer operations, takes less time, filtered through filter beds to remove insoluble particles, sterilized using chlorine, ozone, or UV light to kill bacteria.
Is that for wastewater?
Groundwater.
Groundwater, okay. Chlorine is.
Pardon?
Did you say chlorine?
Yes.
Okay. Okay, chlorine is to clean it up, like to yeah, okay. Take out the color. All right, what next?
Wastewater, more difficult to obtain, takes more time, screening and grit removal to remove large particles,
Okay.
sedimentation to produce sewage, sludge, and aerobic biological treatment of effluent to reduce solid waste.
Okay. Wow. Okay. Okay, that's that. So you can see, there's a lot involved when you want to just even to get the water itself. I mean, the sewage water. It's a lot. Talk less of what's involved in it. Oh, okay. I think You've been able to do justice to this. But you can finish it up on your own, right?
Yes.
Okay. All right. So I guess our next class will be Tuesday.
Yes, yes.
Yeah, but I need a person.
Yes, yes, it should be Tuesday.
All right. So see if you can get another maths question before Tuesday.
Yeah.
Okay.
Muttons is
All
cold.
right. Enjoy the rest of your day.
You too. Thank you, sir.
All right. You're welcome.